Hello, calculus students. This is our first lesson of the second semester, Extrema on an interval. Extrema is basically the idea of a max or min, and we're trying to find the high and low points on an interval. Now here's some of the definitions. Extrema refers to either of these two words, minimum or maximum. F of c is the minimum of f on an interval I, if f of c is less than or equal to f of x for all x in the interval. So when we talk about a minimum, we're talking about a minimum value. That is a y coordinate. So f of c is the y coordinate when x equals c. And is that the lowest possible one? Then that's the minimum. If f of c is greater than or equal to f of x for all x in the interval, then we call that the maximum. These are the extreme values. And we also call this the absolute max or absolute min, or global max or global min on that particular interval. So when we look at this example, it's a small interval on x squared plus 1. Notice that f is continuous, and we're looking at a closed interval. That is, -1 is less than or equal to x is less than or equal to 2. By closed, we mean we're including the endpoints of the interval. As a result, then, we consider 2, 5 our maximum point on the interval because it has the highest y coordinate. And 0, 1 is the minimum because it has the lowest y coordinate. Now, here's the same function, x squared plus 1, but now it's an open interval. That is, -1 is strictly less than x is strictly less than 2, so we're not including the endpoints of the interval. In this case, then, we still get our minimum at 0, 1 because 1 is the lowest value, but we don't really have a maximum anymore, because there's no way to name what this point is just below 5. Because if you think you've got it like 4.9, I'll say, well, 4.95. If you say 4.999, I'll say 4.9999999. So there is no way to point at the exact maximum of this interval. So that's one of the problems with an open interval. In this case, we didn't have a maximum. Here's the same function again, where -1, 2, this is still back to being a closed interval, but somebody has moved this minimum point up to here. And it's defined this way, x squared plus 1 when x does not equal 0, but make it 2 when x equals 0. So it's a piecewise function. Because somebody did that, we no longer have a minimum. Because I really can't call it the point just to the right here, because that doesn't really exist. You can't say the point just to the right because the points are infinitely dense in a real number system. So, here's the extreme value theorem. Notice, look at all three of these examples, and we ended up with a max and a min just in this first example, where we had a closed interval and the function was continuous. If you look at open intervals or a discontinuous function, it's going to wreck this theorem. So, our conditions for the extreme value theorem: if f is continuous on a closed interval a comma b, then f has both a minimum and a maximum on the interval. So let's do some exploring on GeoGebra. You can do this on your calculator as well. And I want you to actually check out GeoGebra this quarter because it does have a nice feature called the function inspector. Let's look at f of x equals x squared minus 4x plus 5 on the closed interval from -1 to 3. So I've got the functions here. Here's our first one, x squared minus 4x plus 5. And you just want to look on the closed interval from -1 to 3 and see what's happened. Well, if you go to this thing right here where a equals 2 and click on it, it's called, it's under ABC. Under the ABC column, it's called, the last thing on is called the function inspector. And we can actually just select this function and then tell it what we want to look at over. Down here at the bottom, notice it'll do a closed interval, and we want to go from -1 to 3. So let's look at that. And it gives us what's going on in there. And when we move this aside too, it kind of shows us. Now I'm going to slide this down here, so you can see the whole thing change the scaling here a little bit. There you go. And now the function inspector tells us some of the key things we're looking at in the function. That we have a minimum at 2, 1. We have a maximum of -1, 10 because it's one of the endpoints of the interval. Later on, we'll talk about the integral, that is the area of the shaded region. And so it tells us a lot about what we're doing this quarter. And we can look at specific points too, but for right now, that's the interval we're concerned with. And notice it looks like it has a maximum at -110 and a minimum at 2, 1. Now notice this minimum is not the endpoint of the interval. We're going to use calculus to find this minimum by figuring out where the derivative is equal to 0. Now let's look at our other function, g. Let's turn f off and look at function g now. And let's do the function inspector on that. Now the function inspector drew a picture, so just hang on a second here. Okay, here's another function, x cubed minus 2x squared minus 3x minus 2. It's cubic, it's got those two turns, and it generally goes from negative to positive. What's going on specifically from -1 to 3? Let's ask the function inspector. And we want to change the interval from -1 to 3. And there we go. Just an interval. Oh, it's on points. There we go. There's our interval from -1 to 3. And we can maybe change the scaling a little bit on this so we can get back to see what's going on. There you go. Slide this up. And we can see that in this interval, it looks like we go a little past the minimum. We got a minimum at 1.86, -8. Looks like we can maybe scroll over on this and see what the rest is. Oh, I know, just make this bigger. There we go. And a maximum at -0.5352, 1.12. So those don't look as crisp as the last time, and we're probably going to find that they're radicals. No roots. And it gives us the area and the integral. And we'll talk about this, why the integral is negative and the area is positive later on. It gives us the length of the thing too. Oh my gosh, lots of information on there. Okay, so in this interval, in this closed interval, here's a demonstration of the extreme value theorem. We do have a maximum here and a minimum down here. Okay, back to the notes. Okay, so here's our definitions of relative extrema. If there's an open interval containing C on which f of C is a maximum, then f of C is called a relative max on f. And you can say that f has a relative max at C, comma f of C. So over here at this hill, we see that 0, 0 is a relative maximum. Even though the function will exceed it over here and get higher than it, in this general neighborhood, in this little open interval, it is the highest thing. So we call that a relative maximum, as opposed to the absolute maximum we talked about in the extreme value theorem. Now, if there's an open interval on which f of c is a minimum, then f of c is called a relative minimum. And you can say that f has a relative minimum at c, comma f of c. So notice this valley here. Notice this is not the lowest point on this cubic, because the cubic will get lower than it over here. But relative to the points on either side of it, it is the smallest thing. So we call it a relative minimum. A relative minimum at 2, comma -4. The plural of maximum is maxima. And so you can have more than one relative maximum, depending on how many twists and turns you have in a function. Another word for relative is local. Local maximum and local minimum. This 0, 0 is the local maximum, bigger than anything in its local neighborhood. 2, -4 is a local minimum, smaller than anything in its little local neighborhood. So let's find the value of the derivative at extrema. In this first example, we want to find this relative maximum. And we want to figure out what the derivative is there to help us see, can the derivatives tell us some ways to find these things? Now, I'm going to pause here to do a little derivative race. That is, when you see a function like this, and you want to analyze what the derivative is at a certain point, is it faster to do it by hand or by the calculator? Now, I've been doing these functions for a long time. Let's see how I do. Okay, we're going to start with by hand on this function. So start the stopwatch, please. Here we go. We've got f of x equals 9 times x squared minus 3 over x cubed. And so I'm going to use the quotient rule. F prime of x equals bottom x cubed times the derivative of the top, which is 9 times 2x minus the top, 9 times x squared minus 3 times the derivative of the bottom, which is 3x squared, all over the bottom squared. So I've got to do, let's see, this is 18x to the fourth minus 27x to the fourth plus 81x squared all over x to the sixth. I'm going to need a little more room. So that's 9 minus 9x to the fourth plus 81x squared over x to the sixth. I want to reduce this a little bit. It'll be easier to evaluate it at 3. So we get x squared we can take out of the top, negative 9. In fact, a negative 9x squared. So that leaves, let's see, x squared minus 9 all over x to the sixth. So we have negative 9 times x squared minus 9 over x to the fourth. And so now when we evaluate it at 3, we get negative 9 times 3 squared minus 9 over 3 to the fourth. And we get 0, because the top is 0. Doesn't matter what the bottom is there. It's not 0. Okay, so stop the stopwatch. We have 0. Stop. Stop the stopwatch. Well, it's 2 minutes basically, right? Okay. There. Reset the clock to 2:02. 2:02. Now let's try it on the TI-89, and I think we'll need just about this much space. Okay, let's get ready to start the stopwatch. Here we go. Gotta get the case off, turn it on, clear. The derivative key is right by the 8 there, derivative, and now the function 9, parentheses, x raised to the 2 minus 3, right parentheses, divided by x raised to the 3, comma x with respect to x, right parentheses, use the with symbol, x equals 3, hit enter, and I get 0. Stop the stopwatch. Stop. 35 seconds. 2 minutes versus 35 seconds. So you'd be the judge on that. And I will let you do this. You've already shown me your ability to take derivatives by hand. But for these applications of the derivative, if you were going to spend 2 minutes just coming up with a derivative, when you could get out the calculator in 35 seconds, well, I think the choice is clear. Now, there's going to be some derivatives that are going to be easier to do by hand rather than take all the time to put in the calculator, and I encourage you to do that. And also, sometimes when you take the derivative and you leave it in a factored form, it comes in very handy. Now, the thing I want to get out of this part of the lesson is that notice how at this relative maximum, the derivative is equal to 0. That's going to be very handy. And notice over here, when you do the absolute value of x, you have no derivative here because the directional derivatives disagree. From the right, it looks like a slope of 1. From the left, it looks like a slope of negative 1. There is no derivative. Even though the function is continuous there, there's no derivative at x equals 0 on the absolute value graph. And let's take a look at this x cubed minus 3x. We get derivatives. Here's a good example of it's easy to do the derivative of this by hand. You get f prime of x equals 3x squared minus 3. And so you quickly see that when you put the negative 1 in, you get 3 minus 3, which is 0. And also when you put 1 in, you get 3 minus 3, which is 0. So the derivative at those 2 points is 0. And this other derivative is going to help us find these relative max and mins. So a critical number now is basically the numbers we're really going to be interested in. Let f be defined at c. If f prime of c, the derivative at c equals 0, or if f is not differentiable at c, then c is a critical number of f. It's a number we want to focus on because it could be a candidate for a relative max or min. Notice here, we got this sharp corner where the derivative doesn't exist, and it turns out to be a relative maximum. Here we got a horizontal tangent line. where the derivative is equal to 0, and that turns out to be a maximum. So the relative extrema must occur at critical numbers. If f has a relative min or a relative max at x equals c, then c is a critical number of f. So that's why we're going to investigate the derivative of these things. So here's our steps. Define the extrema on a closed interval, which is guaranteed by the extreme value theorem. Find the extreme of a continuous function on a closed interval. Use the following steps. Find the critical numbers. That is, when is the derivative equal to 0? F prime of c equals 0 or undefined. Find f at each critical number in the open interval. Find f at the endpoints. So you got to make sure you compare the critical numbers to the endpoints. At least one of these is the minimum and the greatest is the maximum. The least of these is the min, the greatest is the max. And note this study tab. The critical numbers alone might not be your extrema. Always check the endpoints. The critical numbers come from not only where the zeros are the derivative, but also where the zero is undefined. Okay, find an extrema on a closed interval. Find the extrema of fx equals 3x to the fourth minus 4x cubed on the interval from -1 to 2. So we can start with the derivative. Just pause for a little check here. Yep, we are rolling. Start with the derivative f prime of x. This one I can easily do by hand. 12x cubed minus 12x squared. And find out when is that equal to 0. Well, it's not going to be undefined because we don't have any division by the variable. We can factor out 12x squared, leaving behind x minus 1. And we get x squared equals 0, or x equals 0, or x equals 1. These are the critical numbers. The numbers that make the derivative equal to 0. And so we're going to check now the following points for x. The endpoints of the interval, -1 and 2, and also any critical numbers in the interval, 0 and 1. And look at the values of each. Look at f of x for each of these. Okay, now we're going to actually put these into the function. F of x equals 3x to the fourth minus 4x cubed. And if you had this in your calculator, you could just do your trace or your function evaluation. But some of these are pretty easy. You put in 0, that makes 0. You put in 1, you get 3 minus 4, which is -1. 2 is a little trickier there. You're going to get 3 times 2 to the fourth minus 4 times 2 cubed. Notice I'm using direct substitution because synthetic's just going to be too many zeros. So we get 48 minus 32, or 16. And you put in -1, you're going to get 3 minus 4 times a minus 1, so you get 7. So see, we get our max equals 16, and our min equals -1. See how that bears out on the chart. Sure enough, here's our minimum value. Notice we're talking about the y-coordinate with the minimum of -1. And the maximum of 16 up here, the y-coordinate is maximum of 16. Notice at 0 we have a 0 slope, but it's not a max or a min, not even relative max or min. Okay. Here's another example. Find the extreme on a closed interval. Find the extreme of this on the closed interval from -1 to 3. So we'll start by looking at the derivative. Is 2 minus 2/3 times 3 is 2x to the -1/3. And we can set that equal to 0. F prime of x equal to 0. So 2 minus 2x to the -1/3 equal to 0. So 2 equals 2x to the -1/3. 1 equals x to the -1/3. This is 1 over x to the 1/3, or x to the 1/3 equals 1. So basically x equals 1, just cube both sides. So x equals 1 is a critical number, but also consider when is f prime of x equal to undefined. When is undefined? Because f prime of x equals 2 minus 2 over x to the 1/3. So when x equals 0, so we have two critical numbers. At x equals 0 and at x equals 1. And we also have to consider the endpoints of the interval. So here's our considerations for x here. Negative 1 to 3, the endpoints of the interval, and also 0 and 1 as the critical numbers. And let's look at the value of the function of each of these. When we put in 0, we just get 0. When you put in 1, you get 2 minus 3, which is negative 1. When we put in 3, let's be a little more careful this time. We get 6 minus 3 times 3 to the 2/3 power. That's one for the calculator. When we put in negative 1, we get 2 times negative 1 minus 3 times negative 1 to the 2/3. Negative 1 squared is 1, and then cubed is 1, so we get negative 2 minus 3, or negative 5. And let's just check on this value on the calculator. And I'm getting negative 0.24025. So it doesn't look like it makes our maximum or a minimum. So we get a max of 0 and a min value of negative 5. Let's see how we did here. There's our minimum of value of negative 5 and maximum value of 0. Notice a strange thing here that happened at 0. That's where the derivative is undefined. We had that sharp corner. And here we have what's called a relative minimum because it's smaller than things around it. But we were just interested in the absolute max and min of the interval, guaranteed by the extreme value theorem. Notice the extreme value theorem still works on this because it's continuous. Even though the function, the derivative is undefined here, the function is continuous the whole time. Okay, just a little note here on the derivative of absolute value. I said you didn't have to know this before, but now I do want you to understand the derivative of the absolute value. So if we have a function, the absolute value of x, remember, is defined in two parts. It's equal to x if x is greater than 0, greater than or equal to 0. Or it's equal to the opposite of x if x is less than 0. That's why you get these two rays. Y equals x is just that straight line at 45 degrees, but that only applies when x is greater than 0. When x goes less than 0, you get the opposite of x, so you get y equals negative x, you get the decreasing line. Notice what happens then when you take the derivative. When you take the derivative, this slope is equal to 1. So that's why we get a constant derivative of 1 over here. On the left, though, the slope equals negative 1, so the derivative ends up being negative 1. So for f prime of x, the general rule for the absolute value of x is just take x divided by the absolute value of x. This turns itself into a piecewise function, so the derivative will be 1 if x is greater than 0, or it'll equal negative 1 if x is less than 0. So you can remember the derivative in this format, sort of an equation format, or in this visual format, and in this piecewise idea. Notice 0 is no longer included, though, because at 0 itself, even though the function is defined and it's continuous there, the directional derivatives don't agree, so the undefined slope. So I must fix my picture here and actually show big open circles here and here. Open circles. Make those open circles. Because the derivative is not defined at 0. F prime of 0 is undefined. Okay, for our last example, we're going to actually do one. Okay, here's our last example of finding extreme on a closed interval. We have an absolute value function. So when we do the derivative, we can borrow this rule we just talked about here, and we get the function, which is 1 minus x squared, the thing inside the absolute value, all divided by the absolute value of that thing. But then don't forget the chain rule, the derivative of the inner function, which is negative 2x. So now we can find out when is the derivative equal to 0. That's when the numerator of this whole thing will equal 0, or 1 minus x squared times negative 2x equals 0. So we get x equals plus or minus 1 from this, and we also get x equals 0 from negative 2x equals 0. We should also look at when is the denominator equal to 0, because that will tell us when the derivative is undefined. It's undefined when the bottom of the fraction is 0, absolute value of 1 minus x squared equals 0. So that's 1 minus x squared equals plus or minus 0. Negative x squared equals plus or minus equals negative 1 plus or minus 0. So x squared equals 1. We get the same answers again. So we get critical numbers at x equals negative 1, 0, and 1. So we should check on those, but we're also looking over the entire interval from negative 2 to 2. So negative 2 to 2, always remember the endpoints of your interval. We want to look at negative 1, 0, and 1 because those are critical numbers. Also now, we want to look at the value of each of these by putting them into the f of x rule. And don't forget, don't put them back into the derivative, put them back into the original equation, f of x equals 1 minus x squared. 1 minus x squared. So when we do that, let's do some of the easy ones here. You put okay, now we have our critical numbers. We're going to check those and the endpoints of our interval and see what their values are. And let's not forget that the function is actually the absolute value of 1 minus x squared as the original function. So when we put in negative 2, we get the absolute value of 1 minus negative 2 squared. Absolute value of negative 3 is 3. And the same thing happens at 2. You put in 0, you get 1. Put in 1 and negative 1, you're going to get 0. So there's our minimum value. The minimum is 0, and the max is 3, and it happens in 2 spots. Let's check that with a graph. And sure enough, we have a maximum of 3. And notice what I mean by the maximum. The maximum is the maximum value, the y-coordinate. If I ask where does the maximum occur, then I would give the x-coordinate. But if I just ask for the maximum, it's the maximum value or y-coordinate of where the function reaches a peak in that interval. The minimum is 0, and that occurs here and here. The minimum value, the smallest y-coordinate, is 0. Okay? So, that does it. And we'll go on to section 2.